So now this is the graph of the exponential function, as we had said. E to the 0 is 1. It goes to 0 when x goes to minus infinity, and then it goes to infinity when x grows to infinity. Okay. Now this next function is the logarithm. Okay, the logarithm is the inverse function of the exponential. We will see what an inverse function is better in the next video. But what it means is that if I have this, what I mean by this, if I assign a value y to a value x, mapping it by the logarithm, what I mean is that x is e to the y. Okay, so if I have this x and I map it to y is in the logarithm, then y gets mapped back to x with the exponential. Okay. Okay. And so this is called an inverse function. So for instance, well, we'll see that later. The domain of the logarithm is 0 infinity, because, so, and you see that this is the range of e to the x. Okay, and this is a very important property that if you call f and its inverse f minus 1, right? So the domain of f minus 1 is the range of f, and vice versa. Okay, range of f minus 1 is the domain of f. Okay, so in order to see it graphically, what it means is that when I take in the inverse function, I'm just mirroring this function against this line y equals x. So the function is the same. If you look at it, if you turn your face and look at this axis, then this function to the left of the axis is just mirrored to the right. Okay, so what I'm taking is, if I take any value x here, for instance 1, if I want to take the inverse of that, I just go to this line and then go back. Okay, so that's why these two things are mirrored here and in this line y equals x. Okay, and so that's what it means, for this, every point in the domain, what I'm getting is just a point in the range, in the vertical line, and from every point in the vertical part here, I'm getting a value here in the horizontal line. Okay, so if this is x, f of x, this is f of x. Okay, so I'm just changing the values. Okay, that's what this function means, right? And so that's the first two properties. Its domain is 0 infinity. The image of the function is the real, so hence it's surjective, and it's monotonic strictly increasing, so then injective again, so it's the same as the exponential. You can see the function here. Okay, and now the four last properties, they come from the similar properties of the exponential. Okay, so you can work a bit with them. So we have the exponential of 0 is 1, so that means that 0 is the logarithm of 1. The three remaining properties of the logarithm. Okay, so if we call y the logarithm of x, then this means we know that x is e to the y. Now if we raise x to the a, this is the same as e to the y to the a, but because of the properties of the exponential, this is e to the a times y. So now if we take the logarithm of x to the a, this is just the inverse of this, so this is a times y. But y is the logarithm of x, so this is a times the logarithm of x. Okay, so this is property 5. Now if we do for property 6, suppose we have the logarithm of x times y, we call it it z, which means that x times y is e to the z, right? But now let's call the logarithm of x, let's call it e to the u, u, and the logarithm of y, we can call it v. Okay, so that means that x is e to the u and y is e to the v, right? So now we can substitute here, it is e to the u times e to the v, but because of the properties of the exponential, this is e to the v plus b, so that means that z is equal to u plus v. Why? Because the exponential is an injective function, so if e to the z and e to the u plus v are the same, that means that the argument of the function is the same. Okay, so now if z is u plus v, then the logarithm of x times y is u plus v is z. Okay, but u is the logarithm of x and y is the logarithm, and v is the logarithm of y, right? So we have proven this sixth property, and the seventh property is just the same, but using well, you can derive it yourselves using this as a template, right? Okay, so that's the logarithm.